My name is Gabriel Zepeda, and thank you for viewing our presentation for the inaugural year for the ASME University Rover Challenge at Cal State LA. The advisor for our team is Dr. Shen. The layout for the presentation will follow the agenda shown here. We will start with an introduction and background. We'll move into a technical breakdown. Then we will do an assessment and summary. And then we will finish off with the future and next steps of the project. This project was composed of 2 senior design teams shown in the slide. We have 5 electrical engineering students and 5 mechanical engineering students. We were able to combine our teams into one single team, which has allowed us to cooperate and further our research. For many years, Mars explorations has been an interest for humanity. We have sent many various types of spacecraft and rovers to explore and analyze the mysterious red planet that we call our planetary neighbor. There are a few reasons for visiting the red planet, including habitability, researching for the existence of life, and different application. Humans will continue to explore the red planet in hopes of colonization. The University Rover Challenge. The URC originated in 2006 with an objective to assist Mars astronauts. It is held at the Mars Desert Research Center in Hanksville, Utah, and the competition is a part of a series of challenges involving Europe, Canada, and India. Mission and scope. The mission of the URC is the Mars Society University Rover challenges students to build a remotely operated rover that can accomplish a variety of tasks that might one day assist astronauts working on the surface of Mars. The scope, the autonomous navigation. Rovers shall be required to autonomously traverse to post or between gates in the staged mission across easy and moderately difficult terrain. Here are the requirements. As we can see, there is a weight requirement, and then there's also an individual weight requirement. So there are multiple different missions, and there are individual mission weight requirements, as well as an overall weight requirement. The rover must have a kill switch. It has to have a communication distance requirement. There is also a low band and high frequency requirement. There is a base station antenna height requirement, a base station power requirement, and then the rover must be able to survive a moderate set of weather conditions, as well as a battery time limit. Moving on, we have the autonomous mission requirements. For the autonomous mission, the rover must have LED indicators. It must have a QR tag reader. It has to have a GPS locating system. And it must be able to return home. Moving on, we can see the Gantt chart overview for how our project was laid out. We start with our research, which was allocated for the entire team. We have the mechanical engineering under general design, as well as drive system. In the electrical engineering, we have power and communications. And below that, we have the software team with programming and image recognition. So now I'm gonna hand it off to Zori to start with a technical breakdown of the project.
Hello, everybody. We are the mechanical engineering sub-team, and we are going to take a deeper look into the general design. And so in table 4, we can see the Gantt chart in table 4, we can see the Gantt chart for the general design, and where we have the frame and suspension. And the frame and suspension is 100% complete. And now we are transitioning to the assembly phase, where we are 35% complete. And we have some of the pieces cut up and all the machining done, and now all that's left is to put the pieces together. And the last part is the thermal analysis, which is also 100% complete. So in figure 3 and 4, we kind of see a basic overview of what our projected frame and suspension design is going to be. And this design was based off of a Canadian rover team from Carleton University. And the frame and suspension design is the goal for this design was to make it very cost effective and a very simple design, which uses a rectangular frame and it's just hooked up to a single suspension arm with struts. And basically, this design was built off of parts that we had already on hand, provided by our advisor, Dr. Shen. The overall dimensions, currently, the frame and suspension sits at about 45 inches in length and about 25 inches in width. And this design comes with a couple of unique aspects, with one being shown in figure 5, which is the U bracket. Now, this idea came from basically we were having a lot of issues trying to figure out how we can uh, mount the top of the strut to the frame. So the mounting hole on the top of the strut is about 0.55 inches in diameter, with the mounting holes on the frame are about 0.31. Now, we could have just drilled a hole inside of the frame and just ran a bolt straight through, but the best thing about these frame tubings is that it gives us maximum adjustability. So if we didn't like one spot, we would have to move it to another hole, which means that we would have to drill that one out too. And the more drilling that we do is just going to weaken up the frame. So the best way to work around this was to create a U bracket out of a 1/4 inch aluminum, where one side of the U, the frame side, we can drill out holes to accommodate with the mounting holes on the frame, and the other side we can drill out a hole to accommodate the top of the strut. And in the second unique aspect of this design was is shown in figure 6, which the battery tray on under the frame. Now, the reason for this was because we originally wanted to put 4 batteries inside of the component box, but the problem with that is it's going to take away some of the space, which means that a lot of the electrical components, which there are a lot, we were going to end up cramming. And some of the problems that can arise from that is a wire might touch something that it's not supposed to, which can lead to a very bad short in the system, and in turn damage all of the internals in that component box. And the second issue that we had was airflow. We are going to be using 2 standard PC fans to get adequate airflow throughout the component box. And if we were to put the 4 batteries there, it was going to block most of that airflow. So the best idea that we came up with was to actually mount the batteries under the component box, drill a small hole on the bottom of the component box where we can actually route the wires that are going to be coming from the batteries. And that basically sums up the frame and suspension. And I'm going to go ahead and hand it off to Luis, who's going to be talking about thermal analysis.
All right, so for the thermal analysis inside the component box, in electronics, all devices require power to operate. This power comes from both voltage and current provided by a designated source. This energy consumption is converted into heat energy due to the resistance every component implements on the flowing electrons. The rate at which this heat is dissipated is called power, denoted by the letter P, and it is measured in units of watts. Table 5 shows the power dissipation due to power consumption. Note, this table considers maximum supply voltage and current values for power dissipation. Values completely disregard MOSFET dissipation and switching losses. The values obtained from power dissipations were used to determine the maximum temperature every component would reach inside the component box. Since no component is allowed to reach 80 degrees Celsius, the ambient temperature, components' thermal resistance, and power dissipations are all parameters that dictate whether the maximum temperature will be reached. In such scenario, a cooling system will be needed beyond the 2 fans that are already incorporated inside the component box. Now I'll be handing it over to the drive system.
So this is the mechanical engineering drive system subteam. Table 6 shows the Gantt chart for the drive system subteam, where we're tasked with 4 different tasks for finding a motor driver, the wheels, and encoders. And we're 100% done as we chose each of those, and we currently have them with us. Go ahead, next slide, please. Here we have the calculations for the drive system. On the left, we have the force per wheel during acceleration. So this would be the force generated, the acceleration to reach the maximum speed that we decided to give it at 3.5 miles per hour or 1.56 meters per second. The acceleration, to find the acceleration, we have to divide the change in velocity over the time that we wanted it to reach the maximum speed, which was 3 seconds. So our acceleration is 0.52 meters per second squared. Moving on to Newton's second law of motion, the mass is 50 kilograms, which is the maximum mass, or the maximum weight per deployable mission. So the force generated by the rover is 26 newtons. But because we're looking for the force of the wheel, we would have to divide that force by 4. And we decided to introduce a safety factor of 2 to give us some leeway in case the motors don't work up to par. So the force of each wheel is 13 Newton meters. Going on to finding the torque for the wheel for the acceleration, we just multiplied the force of the wheel times the radius of the wheel. And in this case, we used the radius of 10 inches or 0.127 meters. So the torque generated is 1.651 newtons. And we also needed to calculate a maximum torque in case there are going to be obstacles in the way of the rover. So we would need to calculate a torque based off of that. So for that, we would have to divide the weight times. We would have to divide the weight by 4. In this case, the weight is 50 kilograms times gravity, which is 9.81 meters per second squared. So the force on each wheel is 122.5 newtons. So therefore, the maximum torque that we would need is 31.12 Newton meters. And figure 7 just depicts a figure of how we went about calculating the torque. Next slide. And table 7 just lists the drive system components based off the previous slide. So here we have the motor, the motor box, and then the motor driver, and the quantities of how many we were going to be needing. And now I'll pass it off to the electrical engineering team.
Okay, so our electrical engineering team, it consists of Gabe, Zach, Oscar, Frank, and Natalie. Next slide. So my name is Oscar. I've been working on our rover's power and organization of electrical components. In my section of the Gantt chart, you can see the tasks that I have carried out so far, which includes list of electrical components, hardware architecture model, battery selection, power distribution board, component box model, and component box assembly. The component box model and assembly are currently being worked on, and so that's why I have it at 85% and then 30%. We're still working out some of the completion dates since the pandemic has made it difficult to meet in person, but we do hope to complete these tasks before the end of the semester. After coming up with the requirements and expectations of our project, we then made a list of electrical components that would be required. Here you can see a few of the items that we are implementing in our rover, as well as the brand, quantity, and some important power characteristics. Power consumption of each device was important to consider before selection of our power source. We ended up selecting 4 12-volt, 7-amp-hour batteries made by Power King. This decision was made partly because we already had 2 of them on campus, and we also felt it would be sufficient for our project. Next slide. Next, we wanted to know how these components would be laid out and connected to one another, and that is why we created a hardware architecture model. At the top of our model, we have our power source and power distribution board, which then distributes power to each of our devices. We have 2 Arduinos in our project. One controls motors through motor drivers, and another controls our GPS and IMU. And then both Arduinos are communicating with our Jetson computer through a USB hub. We also included a camera, LiDAR, and the required onboard LEDs and kill switch. Next slide. Next, we can look at the SolidWorks model of our batteries. This is in figure 9. We have wired our 4 12-volt batteries in parallel to make one 12-volt, 28 amp hour power source for our rover. And this is output by a yellow connector, as you can see in the model there. The next figure is a SolidWorks model of our component box. And it doesn't have all the components yet, but we have included the Jetson, Arduinos, motor drivers, voltage bus, and USB hub. And there's also wiring that shows our power and communication connections. Yeah, and so now I'm going to pass it over to the communications team.
So my name is Zach, and I headed up the communications team along with Gabe. So far, as our Gantt chart shows, we have completed everything except for the few final tests, and we should be finishing those as soon as we can. Moving to the next slide. So the communication system is comprised of 2 main components. First, we have an access point, and then we have an antenna. So on the left, the access point is the TP-Link TLWA801ND. That's the one we'll be using. And it is 2.4 gigahertz across multiple bands. It's compatible with several 802.11 standards, and it has speeds of up to 300 megabits per second, which should be much more than we need. So this should meet our needs great. Moving on to the antenna, there's 2 main choices as far as antennas. We can either go for a directional or an omnidirectional antenna. We've chosen to use an omnidirectional antenna because the directional antenna brings up new challenges as far as aiming it at the rover or at the base station. And we don't have the expertise or the time available to create that system. So instead, we've gone with an omnidirectional antenna, which should be much easier to use and implement. However, there's still a lot of choices and subtleties within an omnidirectional antenna. So for that antenna, there's 3 main factors. There's the gain, which is basically the added signal strength that is measured in decibels relative to isotope, which is shortened to dBi. There's the frequency, and then there's the directivity, so omnidirectional or directional. As you can see in figure 12, this is an omnidirectional antenna. This is what it looks like, and this is a very similar model to the one that we have chosen. In figure 13, it shows a actual distribution map of the coverage, and it shows that on the left, the blue circle is kind of the horizontal plane, and it shows that there's excellent coverage. On the right, in the red circles, there's kind of the vertical plane, and it shows that an omnidirectional antenna is not like a dome, but it's more of a flat surface. In figure 14, it shows the different effects of different decibels and different gains. So as you can see, with the higher decibels, the less vertical coverage you get at the trade-off of greater horizontal coverage and greater distance. Moving on to the next slide. This is our calculation for how we found that we needed a 12 decibel antenna. So in figure 15, we've calculated the antenna power, and in figure 16, we calculated the antenna range. From the competition rules, we knew how much range that we would like to have, and so using this information, we were able to backtrack and find the decibels of the antenna that we needed. So as it says on the slide, the signal generated by the access point must be at least 12.7 milliwatts to reach the specified distance of 1 kilometer. All right, so moving on, we're going to hand it off to the software team.
Okay. My name is Aldrin Pacquaio, and we will now be presenting a software portion of the University Rover competition. Starting off with the general portion of software. I, along with Frank, Gabe, Nat, and Pac, have been working on this theme. Next slide. This is the finalized software architecture in Figure 17, where the user layer, algorithm layer, platform layer, and driver layer work in unison in order to complete the autonomous mission. This model uses the sensors to control the motors accordingly. I'm going to hand it off to Frank to move on to our state machine.
Hi, I'm Frank, and this is our current state machine, which showcases the process of the autonomous navigation. We start with an initialize, which is followed by the waypoint navigation. From the waypoint navigation, we could proceed to 3 paths, which are obstacle avoidance, search algorithm, and the gate/post. Obstacle avoidance allows the rover to avoid any potential objects in the way. Assuming there are no objects in the way, the waypoint navigation proceeds to find the gate/post. However, if the camera cannot find the QR code, then it must perform a search algorithm. Assuming that the search algorithm is successful, we can then proceed to scanning the QR code and determine if it is a gate/post. If it is a gate, then it is gate code and it is gate complete. If it is a post, then it is post complete. Both the gate code and the post code lead to mission complete. And if the mission is not complete, then we once proceed to waypoint navigation and run through the start of the state machine again. However, if the mission is complete, then we are done. I will now pass it on to Aldrin.
Okay, thanks, Frank. Figure 19 displays how information is sent from one component to the next. The Arduino, which holds the IMU and GPS, the camera, and the LiDAR, will send their sensor information to the Jetson. The Jetson will send information to the motor driver. The encoder will send information back to the Jetson about distance and speed values. The objects in this figure will be displayed as nodes in the ROS program. The arrows represents topics sent from node to node. This communication system will be put together in a state machine that follows a logical approach for the autonomous mission. Arduino to ROS testing was completed. IMU and GPS can send information to the Jetson. ROS to Arduino testing was completed. We're able to send information to the motors for movement. Wireless communication between the Jetson and base station computer is possible. We completed that testing. Testing for camera and LiDAR have not been fully completed, but we have made great strides to that. I'm going to pass it on to Gabe to explain how the software information path of controlling the motors.
So in figure 20, we can see the path of information. The information will start at the base station with the user input on the keyboard. After that, a Python file will receive the input and output an array value. The array value will be passed into an Arduino file, which determines the direction of the motors that the motors need to move. We can now move on to Natalie with the master-slave communication.
Hi everyone, my name is Natalie and we're going to be talking about the master-slave communication. So master-slave communication is a form of communication between two computers in which one is a controller, known as the master, and one is being controlled, known as the slave. In our application, we will have a computer on the rover that will act as a slave, and the computer that we will use to wirelessly control the rover that will act as the master. One of our first tasks, once we were able to establish master-slave communication between the two machines, was to run a popular ROS program called TurtleSim. In figure 21, the screen on the left is the master, where the controls are being sent through the keyboard input, and the controls are then being reflected as movement in the TurtleSim program on the slave computer, which is the blue screen on the right. Next slide, please. I'm going to hand it on to Pac, who's going to talk about our software image recognition.
Hello, my name is Pac, and for software integration, we are about 50% in computer vision to ROS, but we have done we have completed most of everything else. Next. So for the computer software, we decided and researched to use YOLO v4 as the detector and Darknet 52 as the backbone. We were able to train the AR tags provided by the URC website. We used 50 images to train this specific detection software. And in the next slide, you'll see you'll see the computer vision detect the AR code and also output the location of the AR code with respect to the center of the object. So play. Okay, next will be Natalie.
Okay, so we are going to be finishing off our presentation and summarizing what we've discussed today. So for the total progress that we made this year, we have totaled to $2,448.08. Our total weight came out to 85 pounds, which is roughly 38.5 kilograms. So it is far under the limit, and future teams have much more space to work with. As seen in the general and mechanical engineering slide, here's a final rendering of our rover from a couple different views with all the parts attached. Next slide, please. So in summary, we worked on this project to create a rover that will conform to the URC guidelines. The mechanical engineering team completed its general design of suspension and frame and the drive systems. The E team created designs for the power and communication systems. And the software team tested and created programs using ROS that will allow the rover to traverse both autonomously and remotely. So where do we go from here? Here are our next steps. Anything physical that we worked on will be given to Dr. Shen to contribute working on the rover with CSULA's ASME team and future senior design teams. Any software that we worked on has been saved to GitHub with our ownership being transferred to Dr. Shen to share with the same teams. We would like to say thank you to our advisor, Dr. Shen, and to our senior design professor,